Hello everyone, I hope you are doing well. So in today's video, we are going to go through the 2023 chemistry exam, part 1 of the multiple choice section. And so like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And here guys, let's smash through this video. Question 1. Which of the following correctly represents the reaction of glucose in human cells? Now you should realize which one it is. Like you should already realize which what happens in glucose in human cells. It goes through cellular respiration, where basically glucose combusts to give us energy. And now you can say two words. Sometimes it's saying, in a lot of exams, it could say combustion. So glucose combusts or oxidizes. Both mean the same thing, basically. So what happens in cellular respiration is we have glucose, so C6H12O6, in its aqueous form. And remember, just a normal combustion reaction. Remember, you react like a fuel. Imagine this is your fuel. This is your actual fuel. And you react with oxygen gas. Now, you react with 6 oxygen gas. And that results in 6 waters and 6 CO2 molecules. And also plus energy, which is the chemical energy that your cells get from it. So yeah, absolutely, that is your cellular respiration. That's what the reaction your body does in terms of glucose. It combusts it, and hence we receive energy from it. So type of reaction, respiration, absolutely. Hydrolysis, you should straight away realize, why would hydrolysis be there? Look, hydrolysis is, what it does is it takes water and breaks down, peptides, polysaccharides, anything. But the big problem is it won't actually break down glucose, because glucose is the most basic unit of a monosaccharide. It is the most basic unit. Remember, if you have, let's say, two glucose molecules, and they are bonded by, of course, glycosidic linkages, you can actually break it down using hydrolysis. You can break that bond using hydrolysis, which is water. But if you have water itself, one glucose, you can't do nothing with hydrolysis. Can't do nothing about it. It can, it's a monomer. It's the most basic unit. You won't even be able to break it. So absolutely not. So yep, rubbish. So hydrolysis is wrong. So C and D are wrong. Respiration is. And what is respiration? Now think of it. Think of this as a fuel, and it's going for combustion. Combustion, is exothermic. So absolutely, your change in H must be less than 0. It is an exothermic reaction. We are releasing thermal energy and hence energy. So absolutely. So choose 1B. There it is. Let me draw it nicely. There it is. Next question. Let's have that. Which of the following statements is correct? Fuel cells and galvanic cells produce heat. Yes, they do, actually. They do. So we know galvanic cells are, their main function is basically take chemical energy, so chemical, and transform it into electrical. Now, this is not 100% efficient. It doesn't take 100% of all those chemicals and produce electricity from them. That's rubbish. We don't, especially galvanic cells, they are not 100% efficient. It's around 60, if I'm not mistaken, 60% efficient. The other 40% is basically those chemical. It's through chemical that transforms into thermal energy, and that's why it is very insufficient. So galvanic cells are very insufficient because they produce thermal energy, which is hence producing heat. So galvanic cells do actually produce heat. Absolutely. So yeah, let's have a look at the next one. Fuel cells. Fuel cells absolutely do also produce heat. Now, we know that, of course, fuel cells, what are they? They're just basically galvanic cells. And but they are more efficient, by the way. They are much more efficient in a way. So they're I think, around 80% more efficient in terms of transferring chemical energy to electrical. But we still have, of course, that chemical to thermal, because not everything in the world is 100% efficient. So, of course, we still do produce some of that thermal energy. And yeah, absolutely. So fuel cells and galvanic cells actually do both produce heat. So we can put a tick on that. That is correct. Let's check the other ones for a second. Fuel cells have inert electrodes, whereas galvanic cells do not. Rubbish. We've seen galvanic cells have inert electrodes. For example, if you have, let's say, a gas, you want to have a gas, you want to react the gas, we basically, this is what we do. Say we have a beaker here. Draw a nice beaker. That's not nice, but here it is. Wow, what's... Okay, here let's say this is a beaker. Now, remember, electrodes are basically solid. And what about if we want to react like chlorine gas or hydrogen gas? How do we react them? That's where we have to use inert electrodes. How do we use them? Basically, you'd say this is your electrolyte. What we do is we basically put a glass tube here. A glass tube. And this is where basically we put our gas. And hence, we still have to put an inert electrode. Of course, we put an inert electrode here just because we don't want it to react, because we want that gas to react. That's why. So, absolutely, we we have inert electrodes in galvanic cells. Why? Yeah, so why is that? That's rubbish. So, let's take that off. So, fuel cells have inert electrodes. Yes, they do. Also, fuel cells and galvanic cells do not. Yes, they can. Fuel cells, galvanic cells do also have inert electrodes like carbon, graphite. Yeah. See, fuel cells have porous electrodes, whereas galvanic cells do not. Now, yes, fuel cells have porous electrodes. Why is that? Because the surface area is increased. It has little holes, so surface area is increased, so gas diffusion is much easier, and increases the rate of reaction. And it says, whereas galvanic cells do not. Not true. You can actually have galvanic cells have porous electrodes because, for example, you want to increase the rate of reaction. You basically just put, in the electrodes, basically make them porous, and that increases surface area and hence increases your rate of reaction. So, yeah, I don't know what it means by, galvanic cells do not. They actually do have. Some do actually are able to have porous, so... That is wrong. So fuel cells have porous electrodes, whereas galvanic cells do not. They both can have porous electrodes. Also, yeah, fuel cells and galvanic cells operate when electrons flow through the electrode. Rubbish. Absolutely rubbish. Be careful with the wording here. Electrons flow through the external circuit, not the internal. The internal is where electrolytes flow, where ions flow through the electrolytes. Remember that. So, we know when we have, say, I'm just going to basically duplicate this. Whoops. So we have alright. Say we have, this is your, what we call your salt bridge. And so we have the electrolyte itself. You can see that basically the salt bridge is within those electrolytes, so ions can flow. But electrons flow through, say we have two electrodes here. Electrons actually flow through the external circuit. Not wherever the electrolytes. They're not even touching the electrolytes. They're touching the electrodes. So absolutely rubbish. That is not right. So choose A. A is the correct one in that one. Beautiful. Question 3. Molecules X, Y, and Z all have the same number of carbon atoms. All right. So we can see that some just have double bonds, whereas others don't. Yep, this one has 3 double bonds. What is the melting point from highest to lowest for these 3 molecules? All right, easy. Now, you should remember, do you know what we call those, if we have a double bond and there's a double bond, especially in these triglycerides. These are called kinks, and kinks are a big problem because they don't allow the molecule to chain up or to kind of like compress each other. It doesn't. So the intermolecular forces are basically weaker. So having kinks is a big problem. If you have a high number of kinks, your melting point goes very low because your intermolecular forces are weaker. So you can see that the one that has the highest kinks is this one has 3 kinks. So absolutely this is going to be the lowest. Y has no kinks. It has no, double bonds. So this is great. So it's going to be the highest, whereas this one only has 1 kink and hence is the second. So we're going from highest to lowest. Well, the highest is Y because it doesn't have any kinks. X is next and Z is the lowest of the melting point because it has the most kinks. So Y, X, and Z. So 3A. Beautiful. let's have a look at question 4. A cell can be considered a secondary cell if what? Now you should realize, what is a secondary cell? What defines a secondary cell? A secondary cell can basically switch between a galvanic cell and an electrolytic cell. So remember, so what it can do is basically it can switch from changing chemical energy to electrical and vice versa. So it can basically switch between them. That's what defines a secondary cell overall. It has a continuous, so let's have a look at the question. So a cell can be considered a secondary cell if it has a continuous supply of reactants. That's what an actual fuel cell is. Not true. Secondary cells don't require an actual continuous supply of reactants. Because if you think about it, say you have this. So say you start with some chemicals and you start going through, it's a galvanic cell at start, and you're producing electricity. That electricity, let's say it's stored in a battery. And say you finish all those chemicals, say finish your reactants, you finish all of them. And so now you don't have any chemicals. What are you going to do now? But guess what? Because it's a secondary cell, it can go backwards. Remember, it can act as an electrolytic cell and hence create, using all that, electricity from that battery to come back and create more chemical substances, your chemicals. And so basically what it does is it recharges itself. There's no need a continuous supply of reactants. So that's not what really defines it. B, it can operate at different temperatures. Not a really good defining. No, so many things can actually operate different. Fuel cells can operate different cells. So it's not it doesn't define what an actual secondary cell is because it goes through different temperatures. Many things go at different temperatures, and yeah. C, the polarity of the electrodes remains unchanged. Rubbish. When you have a secondary cell, because it can basically switch from a galvanic cell to an electrolytic cell, the polarities do change. Absolutely right. Wrong. So take that off. So they do change. D, it can operate as both galvanic and electrolytic cell. Beautiful. That's what we just said. But that's what basically defines a secondary cell. Choose C. D, basically. All right, 5. Consider the following statements about coenzymes. Now, you guys are lucky because you don't even need to know this. Coenzymes have been taken out of the study design, so skip this question. But I am still going to answer it because just to try to finish it off. Consider the following statements about coenzymes. Coenzymes assist enzymes to catalyze a reaction. Absolutely right. That's what they are made to do. They are able to basically catalyze a reaction. It assists enzymes. Coenzymes bind loosely to the active site of an enzyme. Absolutely, they do. They actually only, not permanently, but they just, loosely bind because they want to, catalyze that reaction and hence leave. They don't actually stay within that enzyme. They actually leave. So they do actually loosely bind to the active site, not permanently bind. So that's also right. Coenzymes act as carriers in transfer of electrons and atoms. Absolutely correct. They do that. That's another definition of coenzymes. They act as transfers of electrons and atoms. So basically all of them. Which of the following statements are correct? All of them. Nice question. It's 5D. 6. Have a look at this. Consider the following statements. HPLC is a qualitative process. Absolutely it is qualitative because, say for example, how can it be a qualitative test? Say comparing retention times. When you have retention times, say you have different, let's say what your retention times gives you is, given that you have, of course, different stationary phases and mobile phases, what the retention times kind of gives you is which one's like more polar or which one's more non-polar. It depends on, of course, the stationary phase and the mobile phase. But yeah, it kind of gives you a qualitative process. It tells you which, if, for example, if say you have a stationary phase that's very polar and the retention time is very long for a substance, that tells you it's very bounded closely to that stationary phase, meaning that it's very polar itself. And hence, if it's more polar, it has a higher melting point because most of the substances that are polar tend to have hydrogen bonding. Whereas if you take let's say non-polar, it was straight away the retention time is very quick, meaning that it didn't really bond with that polar stationary phase. That kind of tells you a lot of stuff. Tells you that its melting points maybe are quite less than compared to the other substances. So it is a qualitative test in terms of substances. So it does, HPLC is a qualitative test. Next one. HPLC is a quantitative process. Absolutely. It can actually also act as a quantitative process. If you actually really think about it, HPLC, if it meant doing it in like a really, what you can do is basically, if you haven't looked at the HPLC, you can actually graph the peak area under concentration. And what you can do is you can find that peak area of a substance, and basically you can say, it's like a straight line. you can actually determine its concentration. So HPLC is a great way in determining concentration. There's many questions of, especially in VCAR, they do these kind of questions where you have the peak area and concentration, and it's a quantitative test. It tells you the concentration. Yeah, so HPLC is a quantitative process. So it's both qualitative and quantitative. It can be used. Next one, triplets give information about a molecule structure. Also true, they do. Triplets, where if you use it in a protein NMR or HNMR, they do tell you about the molecule structure to what's next to it, using the N+1 rule. N+1 rule, if you use the N1 plus rule, you would know what, like your other next to it, how many protons are surrounding that molecule. So yeah, triplets do give some information about the molecule structure. So that's what it's saying. Which of the above statements apply to high-performance liquid chromatography, HPLC? Just the first two. These are the only two. The other one is a HNMR, protein NMR. Absolutely nothing got to do with HPLC. So only the first two. So it's choose C. Beautiful. 7. Let's have a look at this one. Consider the following statements about fossil fuels and biofuels. Production of biofuels does not damage the environment. Rubbish. They do damage the environment. Remember, you need to take land. You need to, if you're growing crops, you need to take a lot of land. You need to give them water, especially in places that don't even have a lot of access to water. That creates a big problem for them. So it does actually damage the environment. So please don't forget, biofuels are not, they do actually do some bad stuff in the environment. So that is, production of biofuel does not damage. Absolutely wrong. So it does damage it. Combustion of both biofuels and fossil fuels generate greenhouse gases. Yes, they do. They generate water and CO2, which are basically your greenhouse gases. So that's correct. Biofuels and fossil fuels are both renewable as they are produced from plants. Rubbish. Fossil fuels, non-renewable, and they are not generated by plants. That's what biofuels are. So 7B, that's the only correct answer. Question 8. At 327 degrees Celsius, the equilibrium constant for the reaction of this is 4.1. What is the equilibrium constant at the same basic temperature, but for this? Now you can see that what really happened is they just doubled the coefficient. They've multiplied this whole thing by 2. So they've doubled all the coefficients. That's very, very easy to do. So what is the equilibrium constant? Now, what do we know? We know that if you double it, you're actually squaring that K constant. So your new K constant is basically the original K constant squared. So if you double it, if you double the coefficients, you're squaring them. If you triple them, you're actually cubing them. So absolutely, that's the pattern. So K is basically, if it's 4.1 initially and you square that, that's going to give you what? 68.8? Yep, so it's not these two, of course. Now, of course, the unit, how do you know the unit? If we're squaring the K value, we're squaring also the unit. So this is the original unit. If you're squaring it, it's going to become m to the negative 4. So choose D as your answer. Question 9. Consider the following statements about coal seam gas and petroleum gas. Okay, coal seam gas and petroleum gas are both mixtures. Yes, they are. Coal seam gas is a mixture of gases like methane, CO2, and a bunch of other gases. So it is a mixture. And petroleum gas are both mixtures. Yes, petroleum, which is also known as crude oil, is also a mixture. Remember, it has gasoline, kerosene, diesel, fuel. It's just a mix of fuels. Yeah, they are both mixtures. So that is correct. Coal seam gas and petroleum gas both combust to produce carbon dioxide. Coal seam gas and petroleum gas both combust to produce... Yes, they do. Absolutely, they do produce carbon dioxide. Okay. Coal seam gas and petroleum gas are both fossil. Yes, they are. They are actually both fossil fuels. Yeah. So which of the following statements are correct? All of them. Beautiful. So 9D. That's a nice, easy question. Question 10. At constant temperature, which of the following always corresponds to the increased yield of a chemical reaction? Let's check. An increase in the value of the equilibrium expression. Okay, so let's say we make a fake reaction. Let's say A. Okay, let's have a look at this. Let's make a fake reaction and test which one will actually create us. Say you have a reaction A plus B, so these are your reactants, goes to making C, which is your product. You remember your K is your concentration of your product over your concentrations of your reactant. And if you're increasing the value of the equilibrium expression, so K, you're increasing K, you're basically increasing your numerator, which is your C, but you're decreasing your both A and B, the concentrations. And hence, if you're increasing your, your C, your concentration of C, you are increasing the yield of the reaction. So if you increase the production of, products, you're increasing your yield, of course. So that is it makes absolutely sense. So that could be the answer. Now remember also K is the extent of reaction. It actually tells us about the extent of reaction. So the higher the K value, it means the more the reactants are basically being produced to product. So that makes sense. An increase in the concentration of reactant. An increase in the concentration of the reactants. Now, there's many ways you can actually increase the concentration. It's not very big. It's not being very detailed because, say for example, you add a reactant. That is increasing the concentration. Or what about you increase pressure of the vessel? That's also increasing the concentration of the reactant. So there's many ways you can increase the concentration, but they're not being kind of very detailed. So let's try them out. Say we add an actual, let's say we add the addition of a reactant, which is increasing the concentration. What happens? If you add A, the system's like, oh my God, that's too much, by the Chantler's principle, of course. So we have too much reactant of A. And so the system's like, that's too much. I need to find a way to get rid of it. It's actually going to go to the right. It's going to go to the forward reaction and hence produce more C, which is great. We are producing more yield of C. But that's the addition of a reactant. What about if you increase pressure? Because remember, pressure is proportional to your concentration. And it makes sense because if you say you have a vessel, and say you have two molecules, yep, you can see that they are basically, okay, the pressure is kind of low here because they're kind of hitting the vessel quite slowly, you would say. But what about if you decrease the volume? The same molecules, the two molecules. Now you have an increased pressure because they're able to basically collide more. And if you want like a basically algebraic expression that kind of describes this, think of it of using your P, V, and RT. We know what? We know that concentration is your N over volume. It's your mole over volume. So if I divide both sides by V, I get this. Where basically, if you look at this expression, this can be, isn't it N over V, which is concentration? So you can actually replace this with C. Meaning that P is proportional to C. That's what we just talked about. It is the proportional concentration. If you increase your pressure, it means you increase in the concentration of everything. Now, if you increase, let's say, pressure. Let's say we increase pressure. Absolutely wrong. We know it be straight away wrong. I just realized that. If you're increasing pressure depends on what the moles on both the reactant side and the product side. Now, because we've just made up an equation, it depends, it could be any equation. So, absolutely wrong. You cannot, when looking at pressure, you need to know what moles are there on the reactant side and the product side. And that's where it's going to go to. It depends if you increase or, So, absolutely, it really, increasing the concentration through pressure wouldn't increase sometimes yield. It depends on the reaction itself, so that's wrong. I would say D is wrong. It doesn't actually always correspond to an increase in yield. C, a decrease in the activation energy. Now look, decreasing the activation energy, which just increases the rate of reaction, that doesn't even increase the yield. Has nothing to do with the yield. Yes, it makes the reaction go quicker, finish quicker, go to completion, but it really doesn't increase the yield, so that's rubbish. Not very good. D, an increase in pressure. Look, like we said, look at it through question B. If you increase pressure, it depends on the reaction that you're looking at. Which one has the more moles or which one has the lower moles? It depends on the pressure. So, absolutely. Like, for example, our one here, if you increase the pressure, the system's like, that's too much pressure. I need to find a way to decrease it. It's going to go to the forwards reaction. But that's only because I made up an equation. It could have been the other way. I could have had, let's say, 4 of these. Then it would be the opposite. So, not true. So, A is the one, basically, that always corresponds to an increase in yield, from what I think. Yeah, whereas the other ones really depend on the, equations or the reaction itself. Question 11. A student conducted an experiment to determine the rate of a chemical reaction. The graph of the student's result is shown, so we can see the concentration of product over time. Which of the following correctly shows the units of the initial rate of reaction? What an easy, beautiful question. Now, you should realize that what defines rate of reaction? Now, the rate of reaction, if you have a concentration time graph like this, it's just the gradient of the graph. The gradient of the graph is your rate of reaction, how quick a reaction goes. So now we know, how would you find it? Well, can you see? What is the gradient of a graph? We know it's the change in y with a change in x. So in this case, you know how we have the, this is our y value, which is your m, your concentration, over time, which is your second. So putting that over s, this is our gradient, or the rate. That's the unit. No, none of them actually have. They're all in mole. So let's convert. Okay, m, which is your concentration. We know concentration is what? Is n over volume. Now, so which is basically mole over liter, which is volume. So we can actually replace this with that. Mole over liter, all divided by s, which gives you mole liter per second. And so you can write that as mole, put those on the top, which is L to the negative 1 and S to the negative 1, which looks like A. Beautiful. Question 12. Consider the following features of a chemical reaction. Activation energy, change in enthalpy of the reaction or enthalpy of the reactants. Compared with an uncatalyzed reaction pathway, the presence of a catalyst changes what? Straight away you should know, it changes the activation energy. It decreases the activation energy for a catalyst reaction. And this is kind of visualize it. It makes sense. So if you actually draw a reaction, you can see that, let's say this is an exothermic reaction. So this is your initial uncatalyzed reaction, and say then after you catalyze it, this is how it looks. Oh, oops. There it is. And not the most nicest, but there it is. You can see that, okay, we can see that activation energy has decreased. But what about your enthalpy change? Your enthalpy change is the same. It hasn't changed for both of them. And so that's not right. Enthalpy of the reactant, so enthalpy is the energy of the reactants. It's the same for both of them. It actually hasn't changed. So the only thing that changes through a catalyst reaction is the activation energy. So only I. So 12A basically. Yeah, so next question, 13. Which molecule can exist as both a cis and a trans isomer? Beautiful. Let's have a look. Let's draw them actually. Graph them. What am I talking about? So the first one is basically a 2 double bond C with bromine, chlorine, hydrogen, and a hydrogen. Now looking at this, it actually can both exist as a cis and trans. It doesn't even exist in any of them, in any of those forms. Remember, a cis is when you have a molecule. Let me draw a nice molecule. A cis is when you have a molecule that is, let's say you have hydrogen here and a hydrogen, let's say you have a hydrogen, say here, and say chlorine and chlorine. This is a cis because what happens is you can see that they are on the same side. Here, you really can see nothing on the same side. Even if you rotate these bromine and chlorine, what happens? Nothing. It's still the same. It doesn't actually exist in that form. What about, okay, so it doesn't exist in the cis. What about the trans? Let's check if it works on the trans. Remember, for a trans, what you need to actually have is, let's say for a trans, you have chlorine here, let's say, and chlorine here, and you have hydrogen here. For a trans to work, what you have to have is basically, have a look at this. You have chlorine on the top side and chlorine on the bottom side, and you can see that they are basically trans. They're kind of different in rotation. Here, again, it won't work. Even if you rotate, you won't get a situation like this or a situation like this where both, yeah, so absolutely that one does not work. It doesn't even exist in those as a cis and trans isomer. What about the next one? Okay, this one absolutely not. I just looked at it. So CC, C, H, B, R, C. This one doesn't even have double bonds. Absolutely doesn't work. As a cis and trans, you need to actually have a double bond. Next one. C. Let's have a try C. So you have a C to C double bond. You have a hydrogen here, CH here, a H, and a chlorine. Okay, we got some good. We can see that there's a cis, like cis works here. We have a cis isomer here, and if you actually rotate the hydrogen, these two here. So if you actually put the chlorine here and the hydrogen here, you also have a trans isomer here. See, the hydrogen, yeah. So this one actually does work. So I'm going to put a tick on that. That looks great. Let's have a look at the next one, D. Okay, we have a C to C double bond here. We have a CH3, chlorine, and a chlorine. And, okay, this doesn't exist in any. You can realize that. There's no cis. Even if you rotate it, it won't even exist. So only C is your answer. What a beautiful, nice question. Question 14. Let's have a try at this one. The equations below shows the equilibrium reaction for the conversion of dinitrogen tetroxide, which is this, to nitrogen this. All right, we can see that it's an endothermic reaction. Which of the following occurs when the temperature is increased from 35 to 80? So we're looking at the rate. Be careful, not equilibrium. So don't even look at the Chandler's principle, rate. Remember, rate is all about collision theory. So when we're talking about the rate, if you're increasing the temperature, you've increased the rate. Now, I think a lot of students do make this mistake. They're thinking that only the forward reaction increases in terms of rate. No, both the forward and the backwards reaction do increase in rate when you increase temperature. So this was a very, very easy question. So C. So rate of the forward and rate of the reverse all both increase when you increase temperature. Question 15. Consider two types of drones, petrol-powered and hydrogen fuel cell-powered. Okay. Which of the following statements is correct about the petrol-powered drones and the hydrogen fuel cell-powered drones? They both produce greenhouse gases. Yes, they basically do, because if you look at a petrol-powered, it probably goes for combustion, and hence you would produce like CO2, H2O. These are basically your greenhouse gases. Remember, water is a greenhouse gas. I think CO2, water, all greenhouse gases. So these here, yep, it does. And whereas our hydrogen fuel cell just produces water, and it is also a greenhouse gas. So yes, it does do that. Only petrol-powered drones produce heat. Not true. Like we said, fuel cells produce heat. They're not 100% efficient where they convert all of it to they don't all just convert basically chemical energy all to electrical. They are not nothing's 100% efficient. They do actually produce some thermal heat. So absolutely, both petrol and the hydrogen also basically produce heat. That's wrong. See, they both have the same energy transformation. Absolutely rubbish. See, the hydrogen fuel cell, the main actual energy transformation that's happening is it's taking chemical energy and transforming it to electrical. Whereas if you look at an actual, what we call and of course there are some, chemical energy to thermal energy in fuel cells because it's not 100% efficient. But if you actually look at it in terms of the petrol-powered is so much more. It has so much even worse, energy transformations. Like, for example, first, you're taking chemical energy and you're creating, when you're combusting it, you're taking chemical energy and you're producing thermal energy. When it combusts, all that thermal energy is taken. And so what that thermal energy is used is it's used to move a turbine. And so that turbine, when it moves, it's moving through mechanical energy now. Now we've gone for chemical, thermal, mechanical. Now what does that mechanical do? It basically moves a generator. It moves a turbine of a generator, and hence that's what creates electricity. So we have 4 energy transformations, and remember, the more energy transformations that we have, the more of a big problem it gets, because we can have energy losses throughout those transitions. So absolutely not. They don't have the same energy transformations. We know petrol powered do have much more of those energy transformations. So they both don't have the same transformations. D. The overall reactions in the hydrogen fuel cells powered are endothermic. Rubbish. It's exothermic. We are producing heat. A. So it's 15A. Beautiful. Question 16. Consider the following molecule. How many peaks will be observed on the carbon NMR spectrum of this molecule? Easy. Let's first have a look at it. All right. Let's draw it in its structural formula. So we have C, carbon here, carbon, and we have a carbon here, carbon, we have a double bond of oxygen, carbon, so carbon and carbon here, we have okay. Now let's just draw these here. All right. And these are the hydrogens basically. All right, here it is. Now, to know how many actual peaks, you need to look at symmetry. If a carbon has symmetry around it, it's a big, you have to think about different ways on looking at it. So let's look at the first carbon. This is how you look at it. Let's look at this first carbon here. Look at the carbon. Does it have symmetry? Look around it. We have all this big molecule on the right, and we have nothing on the left. There's no symmetry, to be honest. You can realize, so we consider that as already one carbon peak. Next one, this carbon here. Look at the symmetry. Look at the left, so it only has one carbon, whereas on the right it has a big rubbish. What the hell is this? Yeah. So there's no symmetry. Again, that's going to be considered as 2 peaks now. If there is symmetry, that's going to change. Next one, what about this carbon here? Look at the symmetry. Look at it on this side. We have 1 carbon. We have 2 carbons here, and then we have a bunch of rubbish here. This is no symmetry in it, and that's going to be considered as 3 now. We have 3 peaks. Look at this carbon here. Again, there's no symmetry around it. That's 4. This one also, no symmetry. Having a look at here and here, there's actually no symmetry. That's already 5. Look at this carbon. Aha! Look at the top of it. That's 1 carbon, and there's 1 carbon on the right of it. There is symmetry. If you look at it, there's actually symmetry. So if there's symmetry, we consider this too as 1 peak. That's already 1 peak. Because of symmetry, they are considered already as 1 peak. So that's 6. And then, of course, this one, 7. So overall, there are 7. Don't forget, people are probably going to put 8 because they just count the number of carbons. Rubbish. Look at the symmetry. Very symmetrical. Like, for example, these 2 here around this C, they're going to be considered as 1. And hence, don't forget this one also, that's 7. We have 7 carbons. So 16C. And yeah, guys, that is it. I hope you guys enjoyed this video and learned something through this. Please make sure to like and subscribe and share this video with your friends. I hope it helped you in any kind of way. And please, guys, take care of yourselves. Bye-bye.